Hello, well in this video I'm gonna talk about the topic 7 of the class, that it's DC on RC circuits. I will start by by explaining the DC circuits, and then I will go to the RC circuits. But everything we know about DC and RC circuits and how we understand them is because of this guy. This guy is called, Kirchhoff. And Kirchhoff gave us some laws, two principal laws. But who is this guy? Well, Kirchhoff was a German physicist, a German that studied physics, and in 1984, he observed that Ohm's laws could be explained through the conservation of energy, and that could be applied to the circuits. And so you could understand more complex circuits and express them in a simple way. So, thanks Kirchhoff. And what's the difference between an DC and RC circuit? The DC circuits are circuits that always have the same current flowing around it. So it's like if nothing was stopping the electron flow in the circuit. And we can compare this, I don't know if you saw my last video, but I was comparing capacitors to banks, where the electron flow or the current was the money and the capacitor was a bank. So whenever the money touched a capacitor, the capacitor stores the energy or the money, and then it can be replaced or it can be dispatched later on. And in the DC circuits, it's like if there was no bank for the money, and the flow, it's always the same. So what's going on in here? It's like if we have the main importance here is that first we saw circuits with only one source of voltage, and here we can, with the Kirchhoff laws, we can understand how circuits with more than one voltage sources, or this term that is EMF, that is the electromotive force, and it's present. So we have more than one battery, and like that. So we could have like two of them. I will try it bigger so you can see it. And you can have one capacitor here, one resistance here, and another resistance over there. And so I will try to explain first what's the electromotive force. Well, EMF, it's the force, the work that it takes you to move one electron from the negative side of the battery to the positive side of the battery. It's not electromagnetic force, it's electromotive force. It's like movement of electron that needs a force. So that's where the name comes from. And once we know that, we have EMF 1, EMF 2. This could have a voltage of 6 volts. This could have a voltage of 2 volts. And the resistances have a resistance of 2 ohms and 4 ohms perhaps. If you saw, I'm using a microphone now. I hope this sounds correctly. And well, the thing is, this is only one loop circuit, and the thing of what when we will go back to Kirchhoff, the thing that he said is that there are 2 constants in every circuit, like 2 constants in life. The first one is that if you analyze, well, I'm gonna build a bigger one here. Let's imagine that we have another side of this with another EMF 3 and another voltage. That bulb is not working that much, and a voltage of 2 volts. So here we have something that is called a node. A node is a point where the circuit separates, and you have one side that it's like this wire over here. You have this wire over here and this wire over here. What it says is that the current that enters the node, well, the sum of the currents that enter the node, it will be equal to the sum of the currents that exit the bulb. So you can say like the sum of currents that it goes in, it's equal to the sum of currents that go out. Or that the sum of the total current, it's equal to 0. Why is that? Because imagine that the node is a point that doesn't store energy. So if I can't save anything, then the things that come to me needs to be released like immediately, because I can't save anything. It's like, we go back to the money example. It's like if in the street, like you're here in the street and these are your streets, this would be the node, and money is coming, and money should continue its way. It doesn't matter if the money is coming over here, or it's coming over here, or it's coming over here, it's coming over here. The money can't stay here. So if you analyze the money over here, and you say, okay, I'm receiving $10, then I should give out the same $10, even though like the money could come this way, $10, and if the 2 exits are here, the sum of exit 1 and exit 2 must be $10. That's like, there's the money can't disappear, and that, as I said before, is related to the conservation of energy. That is how Kirchhoff deduced this theory, because like money, energy can't be created nor destroyed, only transformed, and in this case only distributed. Okay, so once we made that example, we have the first Kirchhoff law, and the second one states that in a loop, this would be a loop. A loop is when you start in one point and you go back to that point. So if I'm here in my house, I have a square like street, I don't know. Here's my house. I start here, I start walking, and if I end up in the same point, then that's a loop. Wait, I lost myself. Yeah, there. Well, that's a loop. here it will be like coming from here, point A, point B. So if I go through like up here and then right and then down and then left and I go back to the same point, the theory says that the sum of voltage should remain the same. So that's like, I don't know how to make that comparison with money, but the point is that if I start here with 10 volts, I will go back having the same amount of money, 10 volts. And that's possible because sometimes you gain volts and sometimes you release volts. You release volts in, for example, resistors, and you gain volts in batteries or electromotive force, EMF. And so how do you analyze if you're losing or gaining? Well, it all depends on the direction of the current. I will make this again. We have this circuit. So at node B, you could have I1 here, I2 here, and I3 here. The thing with the direction of the currents is that the current flows from one node to another, always. And for example, here I3 would be coming here, 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 and it would end here. Alright? And I1 would come here, 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 and it would end here. And I2 would come from here to here. And this is positive, 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 negative, positive, negative, and yeah, like that. So as well, the voltage comes over here. Yeah, whatever. So how you analyze this? If the current is going right ways and the terminals of a battery or of EMF are from negative to positive, then the voltage will be equal to the voltage of the EMF. Right? And if the current is going left ways and the terminals are and the terminals are negative to positive right ways, then the voltage will be equal to minus the voltage of the EMF. Right? Simple? And that's when analyzing voltage. If we are analyzing, well, no, I won't explain that. Then if we were analyzing the resistance, well, the resistors, for example, here, I will locate this resistor over here. The resistors always have inverse signs than the electromotive forces or the batteries or the capacitors. So if this side is positive, negative, positive, the resistors will be positive, negative. So it's the same. If it is positive, negative, then the voltage in the resistor is going to be minus the current. Well, yeah, for example, there, this is I1 minus I1 times the resistance. And here it would be opposite, is plus minus. This would be I1 times the resistance. So that's how you read the voltage flowing through a current, through a circuit. All right, and now well, another thing that we could talk about is how you read these values. Oh shit. How you read those values? Well, there's a thing that it's called a multimeter. A multimeter has multiple usages, and one of them is to measure the amperes, one of them is to measure the voltage, and one of them is to measure the resistance. And so how do you measure what's an ampere? An ampere is the unit for current, and the current, as we saw before, in series it's always the same. So if, well, we connect the amperemeter, we connect it in series. The voltmeter and the ohmmeter, you connect them in parallel. These are the ways to represent it in a circuit diagram. And parallel. So which are the characteristics of these two, well, these three measurement methods? Well, the thing with the capacitor in series, the thing with the capacitor in series is that you will need to have a very, very, very small resistance. It's normally around 1 ohm. So the resistance of the object of the wire does not affect the whole system. And the thing with the voltmeter and ohmmeter is you need to have a very high resistance. So the current would rather go through the, you remember that part? The thing is that if you have a parallel circuit and you have a small resistance here and a high resistance here, it's like a traffic jam, and you have a lot of traffic over here and you have a very small amount of traffic over here. Where would you go through? Well, the same thing occurs with current or with electron flows. It will always rather go through the less resistive way, so it will be easier for it to go through, and that's why you need to have very large amount of resistances in voltmeters and ohmmeters. And well, yeah, that's important, so you don't affect the multimeter when you are measuring voltage and the amperes. And the last thing I'm gonna explain is I've explained DC and RC currents. No, DC, and now I'm gonna explain RC currents. Well, the thing of RC currents is that we now have a bank that is trying to storage the most amount of money that he can or it can. And this circuit can be seen as you have the electromotive force here, then the resistance over here, then I think it's like that, I hope. And the thing is that the current that flows through the circuit will vary over time. So the current that you will be measuring will depend directly on the time, because at time 0 the capacitor will have 0 amount of money, and at time infinite the capacitor will be fully charged. And if the capacitor is fully charged, then there's no current around here. So if we located an ammeter here, remember series, then the current would be 0 over there. Oh, this was T. Sorry about that. And that'll be at time infinite. So a small trick over here that I learned from a guy that explains these things pretty well, much better than me, is that at time 0 you can see this circuit as if the capacitor didn't exist. It was just a wire because it's not charged at all. And another thing that I learned of that guy is that if you have more than one capacitor and more than one resistor, like if you had this, like resistor 1, resistor 2, and then 2 capacitors over here, and this resistor 1 is 2 ohms, and this resistor 2 is 4 ohms, and this capacitors are 2, remember the units for the capacitors? I'll give you 3 seconds. Farads. So yes, this is 4 farads, and well, that's a very large amount of farads. And you have 5 farads. And if you remember the laws of understanding this, if you have a resistance in series, you can sum them. So you have a resistance of 6 ohms, and if you have 2 capacitors in parallel, you can sum them as well. So we have a capacitance of 9 farads, and you still have the same electromotive force. And that's a much simpler circuit to analyze. So that's another tip that I learned from this guy. And where was I? Yes, explaining how to understand, like how to analyze the time in the RC circuits. So there are like much more complex equations to understand this than we had for other examples, like the DC circuits. The thing is that I will only write the most most important ones. with the conservation of energy, the amount of voltage of the EMF that is dissipated, and this is due to the conservation of voltage that Kirchhoff gave us, is the amount of voltage will be equal to the voltage of the resistor plus the voltage at the capacitor. And this will be varying over time, because as the time goes by, the voltage in the resistor, like at time 0, this is will be the max, and at time 0, like time 0, this will be 0. And at time infinite, the voltage at the resistor will be 0, and the voltage at the capacitor will be equal to the electromotive force voltage, EMF. And well, yes, that's one. And you can write that equation without like that's the two opposites. But if you were to analyze a time period, like immediate time period, then you have the voltage. Oh, yeah, the voltage of the EMF minus the current at time t times the resistance minus the charge at time t over the capacitance equals 0. And well, that can be, well, the current at time t, I'm running out of battery, so I hope this ends soon. That'll be equal to the derivative of the time over the derivative of the derivative of the charge times t times the derivative of the time. And so where is he? Oh, yeah, so you could write that also as the derivative dq over dt plus qt over rc equals the voltage EMF over the resistance. Well, that's another equation, and that will help you to understand how the capacitor will be charging and how's the current related to the place in time where you're located at that moment of the analysis. And another thing important is the times constant. The time constant is a constant that relates R and the resistance and the capacitance. And basically what it states is that when you have a very high time constant, then you will need a lot of time to charge the capacitor and also to discharge it. And when you have a low time constant, you will have it will take you less time to charge and discharge the capacitor. So where is that time constant located in the circuits? And battery. In the equation of the charge at the time. So you have that's equal to charge maximum times E minus the time over the time constant, and Qmax it's also the here Qt equals the voltage of the EMF times the capacitance times E minus T over RC. So that's a very important equation that you can use to solve problems. And the last thing I want to show before my computer turns off is the graphs. So if we were to observe how the charge, okay, this is time, this is time, no, this is charge, this will be current. If we were to observe the charge at the capacitor, it would look something like this. And if we were to observe the current in the resistor, it will look something like that. And that, like the gradient, will depend a lot on the time constant. So with a higher time constant, it will be something like that and something like that. And well, that'll be all because my battery is going off. And thank you a lot for staying here for 32 minutes and 5 seconds. Goodbye.